Hello students, welcome back. So good morning to all of you. As you know, last class we studied about the BIOT and SAVART law and how BIOT and SAVART law can be used to find the magnetic field produced by a wire in general, and then how it can be used to find the magnetic field produced by a long wire. Okay, a long wire of finite length. Then we found magnetic field with a infinite length wire. Okay, so with finite length and infinite wire. So we got a very good compact simple expression for both cases, and using that we can find the magnetic field. We can calculate magnetic field due to straight wires. Okay, so the same result we can use for different other applications. That is what today we are going to study. So this was the relation that we got. dB, the small elementary magnetic field, due to a small elementary wire dl. Okay, that is related like this. Okay, the current I is flowing, dB will be equal to mu 0.45 I dl cross r cap by r square. So very simple relation. And if you want to find the total magnetic field, you have to integrate this equation. So that was the procedure we adopted to find the field due to different geometries, okay, different types of wires. And we found that direction will be into the plane of the screen. Okay, in that point. And at any other points, you can easily find the direction using a right hand thumb rule. Okay, using right hand thumb rule, any other point you can find the magnetic field direction. So that's not a problem. So now today let us find magnetic field due to a square loop. A square loop. A square loop means it is a loop made up of wires. Okay, the wire is made into the form of a square loop, and whose sides are given here. Each side is 2r. Its length is 2r. Understand? So each side is of length 2r, and we are interested to find the magnetic field at the point O. That is center point. A current I is flowing through it. These are two diagrams to represent the geometry. How we will find it? We can find easily the value by using our previous result. You can imagine that this coil is made up of 4 wire pieces. 4 wire pieces. Okay, each wire is of finite length, and we already have the equation for finding the magnetic field due to a finite length of wire. We have already derived it. Okay, so that equation is with us, and you use that equation to find the magnetic field due to a single wire at the point O. And you can add up, there are 4 number of pieces. The total magnetic field at the point O will be the magnetic field due to 4 pieces of wire. So let us see how this is calculated. So now I have cut one side. Okay, this is one side and I have cut it, and it is a length 2r, already we know. And we know the magnetic field due to this finite piece at the point O, you can take the point O, will be equal to mu 0 upon 4 pi x I sin theta t minus sin theta. So here our x will be r, and we know this length is r. If this is 2r, this length will be r. So instead of x, we can substitute here r. And what about sin theta 2 and sin theta 1? So we know sin theta 1 is downward and sin theta 2 is upward. Already we have seen. So sin theta 1, here theta is negative. Okay, so theta 1 you can take it as negative. Understand? Whereas theta 2 is positive. So this idea we can incorporate here. Okay, so theta 1 is negative, and you know value of x is r. That can also be incorporated. So what happens? Sin theta 2 plus minus of minus. Okay, plus sin theta 1. And of course this is a square, so both angle will be same. So theta 1 will be equal to theta 2 will be equal to theta. And so what happens? This becomes sin theta plus sin theta, that is 2 sin theta. Okay, 2 sin theta, that is also there. So you can sum up it now. So what we get is the magnetic field at the point O due to this wire will be equal to, you just rearrange this equation. So we got what we get, mu 0 I by 2 pi x sin theta. Okay, symbol modification. Okay, so this is the magnetic field with a single side, single piece of wire. We have how many sides? We have 4 sides, so we have to add up 4 pieces. Okay, so before going into that, we have a theta here. We have to calculate the value of theta from this figure. So this is theta, so sin theta will be obviously this side by hypotenuse, okay, opposite side by hypotenuse. So we get sin theta is equal to r divided by hypotenuse length is r square plus r square root, okay, so that become r root 2, of course. So sin theta will be equal to simply you can by cancelling r and r you get 1 by root 2. So this equation become mu 0 I by 2 pi x into I by root 2. Okay, so just rearrange it to make it all the constants to one side, mu 0 upon 2 pi root 2 I by x. Okay, so that is also there. Now, so what we got now is the magnetic field at the point O due to this piece of wire. So what about if all the 4 sides are taken? You have to multiply with a 4, then you will get the total magnetic field at the point O due to entire wire pieces. Okay, so that become root 2 mu 0 upon pi I by x. Very simple combat equation. So this is a way to find the magnetic field in a square loop. Now you remember I put a randomly x here. You can remove it and instead of that you can put a small r. This side is actually 2r, not r. Keep in mind, and this is r. Okay, this is 2r and this is r, half of the distance. Okay, so instead of x you can put r here. So you got a very combat equation to find the magnetic field at the point O. And the direction also you can find. You take the rotation of the screw direction here. So current is actually flowing in the clockwise direction here. So obviously the direction of magnetic field at the point O will be into the plane of the screen. Okay, that is not marked here. It is clear that the magnetic field direction will be into the plane of the screen. Okay, so that way you get both the magnetic field direction of the magnetic field due to a square ring. Now let us find same BIOT and SAVART law we can use to find the magnetic field with a ring. This is a ring structure. Okay, it is a circular ring or loop of say radius r. Okay, so if you place it like this vertically, so you can see only the sides. Okay, so this is how it really looks like a circular coil. You must have seen in a laboratory, and we will use a symbolic diagram only here. So consider a circular ring, both way it is correct. Okay, this one and this one, carrying a current I. Okay, let's suppose the ring radius, loop radius is smaller. Okay, so then let us see how BIOT and SAVART law we can use to find the magnetic field. First of all, we will go along with this figure. Okay, this ring is now kept perpendicular to the plane of the screen. Okay, so now it looks like this. Okay, so first we will start with the BIOT and SAVART law. dB. Okay, here what is dB? This is a magnetic field at the point O. This is a point P. You can take point as P, and the dB will be the magnetic field at the point due to a small current element here. Obviously, okay, and direction is already well clear. We have made from the previous topic. So direction is like this, of course. So since it is a vector, you can resolve in the component. One component along the direction of the axis of the coil, one perpendicular to the direction of the axis of the coil. Obviously. And what about DL and R cap? DL will be here. If you take the next slide, you will see I redrawn the diagram like this. This is our coil, and we are concerned with the magnetic field at this point P. And so our DL is like this, a red arrow, DL, and the R cap will be in this direction. R cap, the radial vector, unit vector in the radial direction. Okay, this is the distance between the current element and the point P. Okay, so R cap will be the unit vector along this direction. So from the figure it is clear that if you take DL cross R cap, so DL and R cap, the angle will be 90 degree, isn't it? Angle is 90. So DL cross R cap will be obviously, from the figure you get it, DL cross R cap will be equal to DL into R cap is 1 unit, so magnitude is 1, DL into 1 into sin phi, angle is sine. And phi is actually in pi by 2, we have seen that we can include here. So we get dv is equal to mu 0 by 4 pi I dl dot 1 into sine 90, since phi is equal to 90 r square. So we got this relation. So sine 90 is of course 1. So this equation now reduces to a simple form like this. Y mu 0 by 4 pi I dl is only dl here, dl by r square. So we got this. So this is the magnetic field at the point P, due to this small element only. So what about the total magnetic field at the point P? So you have to integrate the contribution to the entire ring. Okay, the entire ring you have to add up. So let us do that. So we have again dB magnetic field due to element, small element dl at the point P. Okay, and you will see that actually this is a vector, this is a dB, and if you resolve along the vertical and the parallel direction, you will see that all the vertical components are mutually opposite to each other, mutually complementary to each other. So they get cancelled and only one component remains back. That will be the Z component. Okay. So we will talk now only about the Z component. Why? All other components, vertical components will get cancelled because they are mutually acting upon each other. Whereas the Z direction, Z component, that will exist. They will not get cancelled. So adding up all the components, you can add up. So initially you do a single element, you can write a dB Z, that is equal to mu 0 by 4 pi I dl by r square sin theta, of course. What about sin theta? From the diagram you can find sin theta will be equal to opposite side by hypotenuse. Hypotenuse is obviously root of z square plus r square. So we can replace the sin theta now with this value. Okay, so we have mu 0 by 4 pi I dl by r square. Sin theta replaced with r by root of z square plus r. Okay. So we got the magnetic field, axial magnetic field due to the current element dl only. Okay, due to the current element dl only. So that is again shown here. We replace this r again. Obviously we know r is equal to root of z square plus r square. So r square is basically z square plus r square. So that is also written. So total magnetic field now you can find by integrating this equation. Very simple. You integrate this equation, you will get the total magnetic field at the point P, and that's actually along the axial direction. Okay, this is also clear. So let us do the integration. So prior to do integration, you can rearrange this equation. You can make it little bit more brief and compact, so that integration becomes much simpler. So for doing that, first of all we multiply these two together, s square plus r square and z square plus r square root. When you multiply these together, you get it as z square plus r square all raised to 3 by 2. No doubt. Okay. Other constants are still there. And now you can see all the other variables are constant except dl. So that will vary from place to place. Okay, dl is varying. So keeping all the constants outside, what do you get? So you add up all the dl components. When you add up all the dl components, what we actually get is you get the circumference of that coil, okay, that loop. And you know loop radius is r. So obviously circumference of that loop will be 2 pi into r. So 2 pi into r is taken here. Instead of integral dl, you take 2 pi r because that is the length of that loop. Okay. So now it's a matter of simple rearrangement. You have a 4 pi here, you have a 2 pi here. So cancelling, you get a mu 0 by 2. Okay, pi cancel. I, then r square, okay, 1 r here, divided by s square plus r square all raised to 3. So we got a compact equation due to a coil. Okay, it's not a coil, it's a loop actually. So and this is the magnetic field, axial magnetic field. Total, okay, keep in mind it's a total axial magnetic field at the point P due to this coil. Okay, so result is obtained. Now you can get some special cases. Suppose you take at the center point. At the center point, you know this distance becomes 0. Okay, that is Z becomes 0. When Z becomes 0, you can replace this with 0. So we replaced here. So now just rearrange it. What happens? We have an r cube in the bottom and r square in the numerator. So they can cancel. So we have mu 0 by 2 into I by r. Very simple form back equation is an extremely proven fact, and by computing this value we get the magnetic field at the center of the loop, okay, center of the loop. So for example, if you consider it as a single loop, then you can easily find the magnetic field at the axis at the center due to, if you know the current and radius of the coil, okay, radius of the coil. So that is the first result. And suppose now you have a, instead of a loop, single loop, you have a coil just like the one shown in the photograph. You can see it consists of number of loops now, okay, 50, 60, 100 like that, depending on our requirement. Suppose in general you take that number of loops are n in number, okay, n can be 1000, 2000, like anything like that. Then total magnetic field at the center will be n into mu 0 by 2 into I. Very simple equation. The previous equation is simply multiplied with the number of turns, okay, n is the number of turns. So the combat equation, you can again, if you want, you can rearrange this, so you get it mu 0 by 2 n I by r. And again another special case arises. Suppose your coil is here and you are talking about a point which is very far away from the axis, okay, very far away from the center. So Z will be very large, okay, Z is very large. So Z is much greater than R. Understand? So what happens if it is like this, Z is much greater than R, then Z square plus R square will become equal to Z square, obviously due to the simple mathematical reason. And so this result you can include here. So what happens, this becomes simply Z cube, okay, this Z cube, Z square, Z cube, okay. So result become mu 0 by 2 I into R square by Z cube, okay. It is not Z square, keep in mind it is Z cube, okay, Z cube. So that is also a result if the point is very far away from the coil. So this should be read as Z cube, okay, then things will become correct. And you can also imagine that if you rearrange this equation by multiplying with a pi in the denominator and numerator, then the above equation become like this, mu 0 upon 2 pi I pi r square by Z cube. So then this will be simply the area of the ring, okay, area of the ring. So how we will write now? So you can write now mu 0 by 2 pi into I into, this is area of the loop, Z square. Actually current multiplied by area of the loop is called magnetic moment of the loop, okay, magnetic moment. It is denoted with the P, letter P, small p. So you can, in terms of magnetic moment, you can write the magnetic flux density at the point P. It becomes like this, mu 0 by 2 pi into P by Z square, okay. So this way you can find the magnetic field due to this geometry, and you can take special cases according to our requirement. So here is assignment. Question is very simple. A circular coil of wire has 100 turns of radius, 100 turns with a radius 8 cm and carrying a current of 0.4 ampere in clockwise direction when viewed from the right side. Okay, find the magnitude and direction of the magnetic field. Okay, so at 2 points. One is at the center of the coil. So you have the equation, you can find the magnitude. So while finding direction, you must be very careful. Okay, so imagine the given data, analyze it, and then only you should find the direction. And second question, at a distance of 20 cm from the center of coil towards the right and normal to the coil. So this is also a case at a distance. Okay, then also you must be careful about the direction. So anyway, you can find both values and you match, verify your values with the given answer. Okay, so do it in a most sincere way. Okay, now let's go to another topic, very simple topic of what is a line integral of magnetic field around a straight current. Straight current means you have a straight wire. Already we have dealt with straight current. Okay, in case of straight current, current is flowing like this, and magnetic field is around the loop. Okay, in fact, you know, if the current wire is straight, the magnetic field at a distance x is given by mu 0 by 2 pi I by x. And these are two diagrams. One is a side view and one is a top view. When you view from top, this looks the wire. Okay, dot resembles a wire, and the magnetic field is around it. Here, current is coming out of the screen, out of the screen. So magnetic field will be obviously anti-clockwise direction. Suppose current is into the screen, magnetic field will be in the other way. Okay, a clockwise direction. So anyway, at any point, you take any point at a distance x, the magnetic field will be mu 0 upon 2 pi I by x. That we know. And suppose the distance instead of x you take it as r, you can write I by r, mu 0 by 2 pi I by r. Okay. Now what we are going to do is, if the line integral of b is taken around the wire at a distance x. Suppose you consider any closed path like this, any closed path. Okay, you know the b at that point. At every point b will be same, as you know already. You can find b at any point. That will be same. What we have to do is, you find the line integral. That means the integral b dot dl. Integral b dot dl. That is called the line integral. Every point you take b and you multiply with the dl at that point. Dl will be naturally tangential, you know very well. Of course b is also in the same direction, so dl is also in the same direction. So naturally the b dot dl will be b into dl into cos 0. Okay, cos 0 is 1. So this will be obviously a scalar quantity. Okay. And on the right side, okay, when you find integral b dot dl, what happens? B is already calculated, that is mu 0 by 2 pi I by r, and dl is this one. Okay, that is given. So what happens? When you integrate, you find that all these values, all mu 0, 2 pi, I, r, etc., all are constant except dl. Dl vary from place to place. Okay, you are integrating the whole path. So what happens? dl, you will find that it is equal to 2 pi r. 2 pi into r, length of this path. Understand? So what we get? When you put a 2 pi r integral instead of integral dl, 2 pi r cancel. So finally we get integral vector b dot dl is equal to mu 0 I. Okay, so here actually left hand side is also a scalar, because b dot dl, I have already told you, we get a scalar value. So in direction wise, magnitude wise, they are equal. So this equation itself is called Ampere's circuital law. The name of this equation is Ampere's circuital law. Okay, this is a very important law in electromagnetism. This can be used to find the magnetic field of certain wire geometries in a simple manner. Using BIOT and SAVART law, of course you can find magnetic field due to any wire, but in a much simpler way, you can find magnetic field due to many wire geometries using this equation. So that we will see in the subsequent slides. Okay. So before that, the previous equation we can define. Okay, this was the equation, and you have to define in a special way. So it is defined like this. It is defined that closed line integral of magnetic field density along an imaginary closed path is equal to the product of the current enclosed by the path and permeability of the medium. Okay, so this is the definition given to this equation. Okay, and here it relates, the line integral relates with the current enclosed by the closed path. So we can see little bit. Let's try to get a little bit more information about this law. We can little bit generalize this equation. This I is actually the current enclosed by the closed path, in fact. So the current can be any number of currents. Okay, not only I. Suppose there are a number of wires passing through it with the currents passing in the upward and downward direction. Then this will be modified. Okay, this become modified. Depending on the current, you can take directions. Suppose current I1 and I2 moving in the upward direction, I3 in the downward direction. So then you have to take the sign of that current also. This is called algebraic summation. Algebraic summation means taking into account the sign of current, whether flowing positive or negative direction like that. So this is the case of a 3 line of current. So if there are n number of currents, you can generalize this part. Current part you can generalize. You can write a line integral b dot dl is equal to mu 0 times summation ii. This I can go from 1 to infinity, okay, any number of values, okay. So this summation actually means algebraic summation, okay, where sign must be taken in account. They are not simply addition, they must be counted, okay, the sign must be accounted. That is why this example is shown here. So again, a more generalized perspective is shown here, okay, a diagram with numerous types of current, number of current in different directions. Then your Ampere circuital law can be written like this. With this summation, now take this form, assumes this form, okay. So from that explanation it is clear. So this is the general form of Ampere circuital law. The law states that the closed line integral of magnetic field density along an imaginary closed path is equal to the product of the algebraic sum, okay, algebraic sum of the total current enclosed by the closed path and permeability of the medium. So mu0 is the actually permeability. Suppose you are talking about a medium with a permeability mu, then instead of mu0 you can add a mu also simply, okay. So that value depends on the medium you are talking about. So this is about a general Ampere's law, okay. It has so many applications. It is useful to find magnetic field due to different symmetrical current. We will see in the subsequent lectures in modules how this can be used to find the magnetic field due to different geometry, like a ring, a loop, or a toroid, or any such symmetrical structure whose magnetic field can be easily obtained using this law. And even BIOT and SAVART law you can derive from Ampere circuital law. So one of the surprising aspects of Ampere circuital law, you can derive it. And another important thing is that BIOT and SAVART law is based on experimental facts, whereas Ampere circuital law is a mathematical relation. That means this relation is mainly used, is a theoretical one, still it can be used to find many other parameters of a current carrying object, okay. So these are the remarks that we want to make in this module. So try to watch this video at least 2 times so as to get all the details, and as far as possible you try to make a brief note of all this. In addition to the assignment that you have to do anyway, in addition to that you do a complete note of the whole lecture. So with these comments, let us stop today's talk. Thank you all.